In this presentation, I'm going to talk about VQVDB, a deep learning powered compressor for volumetric data. It's a very fancy way to say that it compresses and decompresses OpenVDB fog volume. My name is Enzo. I'm a software engineer freshly graduated from university and working at AWS. In my spare time, I do research in machine learning and GPU optimization workflow for Houdini. I recently started a project called VQVDB, which is a technique that compresses volume using machine learning. I posted a quick video on LinkedIn and it went quite well, so I'm going to show you this video now so you have an idea of what VQVDB is. In this presentation, we will talk about the current state of VDB compression and VDB file format, such as NanoVDB, NeuralVDB, etc. I will then talk about VQVDB internal working, how does it perform, what kind of performance we can achieve. I will also do a live demonstration using Houdini SOPs that I implemented, and then we will talk about the future for artists using this kind of machine learning tool. Let's talk about the current state of VDB. The industry standard is OpenVDB. It's using a sparse tree approach in order to divide space and reduce to dense 8x8x8 voxel called diff. It can produce very heavy file cache, especially for sequences, achieving easily terabytes or tens of gigabytes for smaller VDB sequences. The creator of OpenVDB created NanoVDB, which is a linear form of OpenVDB, especially useful for GPU. It adds quantization, which is some sort of compression, and can reduce up to 3 or 4x the footprint of the file. NeuralVDB is created by NVIDIA and used neural networks at different levels in the hierarchy in order to achieve huge compression ratio, but it's very slow to compress and decompress and it's not fully open source, thus not really usable for artists. Let's introduce VQVDB. It starts from a weekend project after watching a video about variational autoencoder. It's a machine learning technique also used in generative AI in order to create new image from data sets. There's a variant of variational autoencoder called vector quantized variational autoencoder. It's used in VQVDB and aims at reducing VDB file size while maintaining a responsive enough compression and decompression time. It's open source, available on GitHub, and the paper is also available on Fixture. The paper is not up to date as there were significant changes in the architecture since, but it gives a pretty good overview on how the technique is used and applied to VDB. Since this tool is designed for artists, I wanted to make the most simple possible pipeline in order to compress and decompress VDB volume. As you can see, there is only two nodes, one encoding and one decoding. You can simply input the VDB into the encoding, it will compress the file into a .vqvdb format on disk, and then you can use the decoding node in order to pick that VQVDB file and decode it straight into Houdini. Let's open Houdini and see how that works in practice. Okay, so we're in Houdini. Let's compress a VDB sequence. Start by creating a geometry node. We can then import a file that contains our VDB sequence. The entire sequence is 129 frames long and weighs 720 megabytes. Let's import it. It's a bit sideways, so I'm going to transform it first. Oh, wrong. There we go. Okay, it looks good. What's in the volume? Just the density field. Voxel size is 1, so nothing to change, it's pretty standard. Let's use the VQVDB encoder. This node's use the file name, which will be appended at the end of the output path for each file. I specify the $F here in order to change the frame number, which will convert this to a VDB sequence. The batch size is the size of the batch that you want to pull in the GPU. I use a 1080 Ti, so in that case, since it's a small VDB volume, I will use 124. You can push this parameter as far as you want, as far as it doesn't exceed your VRAM. Let's connect this. I want to encode the frame range. For this demonstration, I will encode 72 frames. So let's set 72 here. Now we can just click here and click the button encode and save to disk. It will pop up a little Houdini console window with which you will see each frame being compressed. You can also follow here. Each frame takes around 162 milliseconds in order to be compressed. Now let's watch on disk. We have our VDB sequence here, and then we have our VQVDB sequence. As you can see, frame 71 weighs 350 kilobytes. If we look at the VDB, frame 71, 6,616 kilobytes. It's a huge reduction in file size. Now, let's use the decoder. The decoder takes an input the VQVDB file. So we can go look to our VQVDB, show sequences as one entry, and pull that. The batch size works the same way as the encoder, so let's put 124. We can now see our decoder decoding the VQVDB file live. We can then press play and watch the decoding happen in real time. Let's take the frame, this one, great. Now, if you want to compare this and our ground truth set here, or here, it's the same one, we can just set a switch in order to be able to visualize them more easily. Let's switch between the two. You can see little to no difference, which is what we want. Let's get a bit technical now. So VQVDB uses machine learning technique. It means it has to be trained. For each dense leaf in a VDB volume, I run different convolution, channel attention, and residual block steps. Then I create a latent space with 128 dimensions. This space will pick up every detail in each leaf. The training step then compares the input leaf to the reconstructed leaf from the latent space and compute an error metric, usually MSE or LS1. The autoencoder will after that optimize its latent space in order to reproduce a leaf as close as possible to the original. The entirety of VQVDB has been trained in a single GPU, a 1080 Ti, and it uses approximately 50 to 60 gigs of RAM. The compression comes from the discretized latent space. With 256 entries, it fits in a single byte. Let's say we run convolution steps on the leaf and reduce the 8x8x8 to 4x4x4 and keep a single byte in each. We have 32 bytes per leaf, with which we can have near lossless reconstruction, with a 32x smaller memory footprint. The training can easily be done within Houdini using PyOpenVDB to extract leaf data and PyTorch to execute the whole machine learning algorithm. The training process exports an ONNX file, which can be then loaded into the custom C++ application. Houdini is shipped with ONNX, meaning that you can use your GPU and CPU in order to compress and decompress volumes as fast as possible. Now let's look at the quality. So in this A/B comparison, we can see the Disney Cloud full resolution, which is on disk approximately 2.3 GB. If we switch between the two, we can see absolutely no difference. I promise you that those are two different renderers. I know that the render is a bit noisy, but let's look at the next image, where we can see in details that there is very little to no difference. You can see on the left side we have our VDB. When loaded into Houdini, it weighs approximately 3.8 GB. It's loading in 16 seconds on my SSD using Windows. I rendered only a small part where we can see different details, some very dense area and also very wispy and low density area on the bottom. I zoomed in the low density so you can see how it looked. On the right side we have VQVDB. On disk it weighs 138 MB. It loads in 13 seconds. Now you may wonder, how can it load quicker than the VDB one? As I showed in Houdini, we can specify a batch size. Depending on your GPU, it's much faster to load data from the CPU to the GPU than from the SSD to the CPU. Since VQVDB is very small, it can entirely fit in the GPU in one step and then be streamed and decompressed in real time. So it's visually identical and dramatically lighter, at least on disk. When loaded and decompressed, it should be around the same size in RAM as the original VDB. Why did I build VQVDB? Nowadays, I believe that freelance and amateur artists have some kind of gamer workstation, meaning that they have big GPUs. It's almost necessary when working with Houdini or any other tools. GPUs are becoming faster and faster, which tremendously helps the decoding of VQVDB. Since VQVDB file size is smaller, it's also way easier to send them through network. As you can imagine, VQVDB is in very early development stage. You can check out the work being done in real time by checking the GitHub page. As a reminder, VQVDB is open source. Some of the current work includes sequence encoding that can reduce up to 100x VDB file sequence by using temporal coherency. This does not include any machine learning or AI algorithm, similar to what codec like H.264 does. Before finishing this presentation, I would like to thank all the early testers of VQVDB. Without them, I wouldn't have been able to solve all the pesky bugs and distribution issues I had.